I'm going to give you a quick exam review here for the exam on momentum. And of course we have this definition of momentum where we say that momentum, we use a lowercase p to represent it, is just equal to an object's mass times its velocity. So momentum is kind of a measure of how much is moving, how fast, and in what direction. Okay, so if two objects have momentum, they can have the same momentum and be moving at different velocities if they have different masses. But the product of mass times velocity has to be equal. For example, a bullet can have the same momentum as a car, as a moving car. They have to be moving in the same direction. And the bullet, because it has such a tiny mass, it has to be moving much faster than the moving car. But they can have the same momentum. Okay. Now, this all derived from this expression right here. The net force on an object is equal to the rate at which momentum changes. This is actually Newton's second law. It's just that when you have delta, the change in momentum here, this is mass times v final minus the mass times v initial. This is just assuming that the mass is constant, right? And so you just factor out the mass, and you get v final minus v initial over delta t, right? And here's where you get, well, what is this? V final minus v initial, that's delta v. You have delta v over delta t, that's acceleration. And this is where we get F equals m times a. But now it's expressed in terms of momentum instead of velocity and acceleration. Okay. Now, there are certain things that we learned about this. We took this equation right here and we rearranged it, and we said the net force acting on an object times the time that net force is applying is equal to the change in momentum of the object. And we called this the impulse momentum theorem. And I'm not going to, you know what, I shouldn't use a, people are going to think that's a division. It's the impulse momentum theorem. And it says, hey, force times time, we define that to be impulse. Delta P, we define that to be a change in momentum. So, there will be a problem on the test where I give you a net force and I give you a time, and you have to figure out the change in momentum. From the change in momentum, you may have to figure out the change in velocity, or if I give you the initial velocity, you may have to figure out the final velocity. Okay, so there will be, I call those impulse problems. There'll be at least two impulse problems on the test. One of them is just kind of a straight use this equation right here. The other one will be from the graph, kind of like what you did on the take-home test. I'm going to give you a graph. And if I give you force, this is the net force acting on an object, and this is the time that it's acting, and maybe I'll put values on, I will definitely put values on here. And I don't know, I'll give you a certain graph. Well, the area, anytime you have a product, this times this, right? It's a product. Well, the area underneath that graph gives you the third quantity. This is delta P. This is a change in momentum. It's the impulse. It's also the change in momentum on that object. So maybe I'll give you a graph. Use the area of that graph to figure out the impulse. Use the impulse to figure out the change in momentum. Use the change in momentum to figure out the change in velocity. Okay? Now, what if I've got, what if the net force acting on your system is 0? If the net force is equal to 0, Well, that means delta P over delta T is equal to 0. Right? The net force is equal to the rate at which momentum. That means momentum isn't changing. So if delta P equals 0, you just cancel out, multiply both sides by delta T. And what happens is you get a P initial equals P final. So if you've got a system of objects where there is no net outside force acting on that object or on that system of objects, then the total momentum is conserved. This is conservation of linear momentum. So, the initial momentum equals the final momentum when the net force equals 0. Now, when does this happen? Well, it happens in a collision. Let's say I've got two objects, like the little buggy cars, or not buggy cars, but the little cars that we played with. And maybe this one is moving, and this one's at rest. Well, when they interact, when these two cars come together, when they interact, bam, they apply equal and opposite forces to each other, right? So if you include both of them in your system, then those objects, then the net force, there's no net outside force acting on your system. And what that means is that, if this is object 1, it gets its momentum changed. Object 2 gets its momentum changed, but the change of momentum of object 1 is equal but opposite to the change of momentum of object 2. So that when you add them together, you get 0 overall change of momentum for the entire system. Okay? So if I give, and I will give you a couple of different collision problems. If I give you a collision problem where two objects come in and they could hit and then bounce off of each other, or they could hit and stick together, then you can say that this is that the forces that they apply to each other to change their momentum are internal to the system. Internal forces don't change the momentum of the overall system. It's like my least favorite idiom in the English language or expression or whatever is to lift yourself up by your own bootstraps. Have you heard that before? Lift yourself up by your own bootstraps. You haven't heard of that? Oh my gosh. You guys, what kind of education are you getting at this school? All right. You will hear that expression someday, like, lift yourself up by your own bootstraps. You can't! It is physically impossible because the force you apply to your bootstraps, you pull your bootstraps up, your bootstraps pull you down. And the two forces cancel each other out because you are in the same system as your bootstraps. Okay, that was a really stupid example. But you've got this. So here's what you do when you have a collision problem. You say the initial momentum equals the final momentum. I want to see you write this down. And then you look at the problem. And I say, oh, this one's at rest. So this object doesn't have any momentum. This object does. So I'm going to say M1 V1 initial. Now what if this one was moving to the right? Well, then you would have to include it in your equation. Also, make sure that, what does this mean about the velocity of object 2? If I gave you a velocity to the left, when you plug it in here, you've got to make it negative. Anyway, equals, M1 V1 final plus M2 V2 final. What would happen if these two objects, if you had a system a setup like this, and they came together and they stuck together afterwards? What if they're stuck together afterwards? What does that mean is true about their final velocity? Huh? If they're stuck together, what's true about their final velocity? What's V1 final and V2 final? They're not zero. They're equal to each other. They're the same. So if they're stuck together, if you have two objects that were stuck together, let me give you an example problem. Say I give you a car. Maybe we'll do a head-on collision here very soon. If it's a Tesla, though, you'll survive. Okay, there's this one, there's this one, M1, M2. But then afterwards, after the collision, here's the two cars. Okay, here's, all kinds of stuff. But they're moving together. Maybe this one has a greater mass, so maybe they're moving together like this. So you go M1, V1 initial plus M2, V2 initial equals M1 plus M2, right? All the mass is there. We're not going to let any parts fly off the car, the two cars, times V final. They have the same final velocity if they're stuck together. Okay. Now another kind of problem I can give you is where we have elastic collisions. In an elastic collisions, the initial kinetic energy is equal to the final kinetic energy. Then we have inelastic collisions. And in an inelastic collisions, the initial kinetic energy will be, not equal. I'm trying to go too fast, see? Will be greater than your final kinetic energy. So you're going to have a loss. I might ask you, what percentage of the kinetic energy was lost? If I do that, then you can say, well, the change in kinetic energy over the initial kinetic energy times 100%. That'll give you the percentage of the kinetic energy that was lost. Almost all collisions that happen in the macroscopic world are inelastic to some degree. Then you have explosions, and that's what we did with the cars in the lab. The explosions. That's when the initial kinetic energy is less than the final kinetic energy. So I might ask you to do this and find out how much energy was stored in the spring or something like that by looking at the final kinetic energy. But in all three cases, all three of these, P initial equals P final. So, last thing. You're going to have like maybe 4 problems. You're going to have impulse problems where there is a net force on your object. And in the net force, that force times time, that impulse will equal the change in momentum of your object. Then you will have problems where the net force is 0 on your system, and so that the momentum before and after the interaction is conserved. And then you can have inelastic, that is, you're going to lose kinetic energy. Elastic means your kinetic energy stays the same. And then explosions, you had some kind of energy stored up in your system, like a grenade or something, and it blew up, and you ended up with more kinetic energy than you started with. Okay? So it should be a little bit shorter, a little bit easier in the last test, I hope. Any questions? No. That is... No. 1, 2, 3. That is... Finally.